As was said, my name is Sarah Cadieux. I'm kind of skimming the participants to see if Allie is here, but I'm hoping that Allie Wist will pop on. She is a PhD student in the Electronic Arts program at RPI. Many of the images that you'll see today were taken by her, including the one in the background. So I'm hoping she'll pop in and be able to say something about these images. She can speak a lot better to that than I can. I can speak a lot more on the science part of it. But what I really hope to talk about, or hope by the end, what we talk about is that including scientists in including artists in our science is really fruitful. And we had the talk about the Mohawk recently, and I think there were great conversations about that. And there's a lot we can do to include artists more in our work. And I've just learned a lot from being able to do that. So every time I talk about microplastics, I always like to start with just a little background about plastics. So plastic, when it first was invented, was considered a wonder material. So after its discovery, the first application was insulating radiator cabling during the Second World War. But it wasn't long before consumer products soon followed. The plastic shopping bag we no longer see as much around in New York, Tupperware, to artificial hip and knee joints, blood plasma bags. There are so many things that plastic has made possible in the world of medicine, in our everyday lives. But as I'm sure everyone is aware, now we have all of these single-use plastics as well. So first patented in 1973, the PET bottle had many advantages over glass. So it was designed specifically to contain pressurized carbonated drinks. Some of the advantages over glass is that it's lightweight for transport, it's safe in that it's virtually unbreakable, and its popularity as a container for beverages and really for water has boomed in the 21st century. The economics of mass-produced single cheap plastic products has led to this single-use culture. And today, around 500 billion PET bottles are sold every year. So whereas we started with plastic being this wonder product that allowed us to do all these things we weren't able to do before, it was really revolutionary in World War II. Now, what made plastic so great to start with, that it was indestructible, hard to break down, is why we have the issue of microplastics. So as our global plastic production is exponentially increasing, and I made this kind of small because I didn't want to have too many slides, but you can just see over time, going back to 1950s, plastics are increasing to the point that there's plastic everywhere, probably around each one of us right now. If I look to the side, I have my kids' toys, tons of plastic everywhere. And it's the chemical properties that made plastic incredibly useful and durable that is making it difficult to dispose of. So some types take thousands, even tens of thousands of years to degrade in a landfill. So the materials are these persistent organic chemicals that take a long time to break down. And many of our plastic problems began in the post-war period, when we started to not only be using plastic for hospitalizations and all these other uses, but we started to replace paper, which was more expensive, glass and metal products, things that were used as throwaway items, to consumer packaging. And so now we have this issue of plastic everywhere. And all plastic eventually will become microplastics over time. And so I want to give you a sense of scale, because microplastics are something we really can't see. We hear a lot about them, and a lot of this work I'm going to show you is the visualization of these invisible particles. So when I talk about microplastics, what we're talking about is the 1 nanometer to 5 millimeter size. The 5 millimeter size is something that you could see, like your hair is around that size, pollen, but then as you get smaller, you're into the realm of red blood cells are in that size category. When you're dealing with a plastic straw, that's in the macroplastics. Length of rice is like right on that boundary between macro to micro. And then now we're hearing more and more about the nanoplastics, smaller than 1 nanometer, getting down to the atomic size level. And then when we talk about plastics, there's lots of different categories we can put them in. The ones I'll talk the most about are going to be the fibers. So that's what's coming from our synthetic clothing. There's also pellets, fragments, just little broken pieces, and films coming from plastic bags. So all of these images are giving you an example with a 0.5 millimeter scale of what is the actual size of these particles. So due to their size and density, microplastics, when they break down, are able to travel by wind, in water. They're cycling with the hydraulic cycle. They are in bubbles. So one of the projects I work on a lot is with methane gas, and you have bubbles, ebullition of methane that go into the atmosphere. These bubbles can also contain plastics within them. They're in the air, they're in our rain, they're in our clouds. They're all around us. And so some just extreme examples, I'm sure everyone's heard of some, is these are just some of the ones that really pop out to me are pieces of microplastic inside of zooplankton. And also microplastic here is a fiber, a pellet, lots of fibers here, some fragments, and this is an Arctic sea ice. So microplastics are being identified all over the world, far away from where they were originally used. All right, so the project I'm going to be talking about is focused on Troy, New York. And this project is in collaboration with the Water Justice Lab, which is part of the Nature Lab at the Sanctuary for Independent Media in Troy, New York. So I'll talk about Water Justice Lab in just a little bit. But when he started this project in 2023, what we were thinking about was if we were going to send community scientists out to sample waterways, what is the volume of sample that would be needed? And could we do grab samples? Does it have to be net sampling? Those were kind of the big questions to think about sampling protocols. And then the others were, are there sources of microplastics to the reservoir that we get our water from here in Troy? And are they in our drinking water? So we were using those two questions to then get to also the sample. So we collected lots of different sample volumes in order to address both elements of these questions. So the Water Justice Lab is a group of high school youth science fellows. There is a focus on including youth historically excluded from the sciences. These science fellows process upper Hudson River samples from tributaries for Riverkeeper. They process this for Enterococcus. That data is available on the Riverkeeper website. So if you've ever gone onto their website, into the water quality database and looked at the tributaries for the upper Hudson, those samples were processed at Nature Lab by the youth science fellows. They also take part in a source to estuary camp. So for more information on this program, there is a QR code that will bring you to the Water Justice Lab website. Here's an image just of the fellows from 2023, the ones that were a part of this project. And you'll see their images throughout. And for more information, questions about this, to learn about this program, I would recommend reaching out to Ellie Irons. Her email is here. She's the community science educator and lab manager at Nature Lab. So the summer camp that the students are doing, in addition to processing the samples for Riverkeeper, is called Source to Estuary. So students are learning about our drinking watershed. And so drinking watershed is thinking about how water moves from creeks to streams to our taps and back out again through the sewer system. So here in Troy, we get our water from the Tomhannock Reservoir, which has three main tributaries entering into it: Otter Creek, Susquehanna Creek, and there's a Tomhannock Creek. From there, it goes to our drinking water treatment plants to go out to Troy and other surrounding areas. And this also just shows you some of the other locations that the students went to, as well as the water treatment plant. So as part of the camp, they go to these different locations. You can see in the image, they're on a solar powered boat down in Albany. This is part of Radix, so they're on the Hudson. And in the bottom image, we are, you can kind of, I'm kind of hidden in the back, but we're at the drinking water treatment plants. They also go to the wastewater treatment plant as well. So just to show a little bit of an example of how the sanctuary brings media, science, and art together, I'm going to play a short trailer from a longer film called Echoes from Lock 1. So this video is about maybe 10 years old now. It was made before Water Justice Lab got started, and helps set the context for youth-centered water research. Oh.
We live along the shores of the Hudson River at the beginning of the Erie Canal.
It's playing double time. Let me see if I unmute one. Maybe.
Lock 1.
The United States really gained a lot of wealth in the world by basically dumping their waste away. Well, now we are dealing with the waste.
Calling the Troy lock, requesting passage north.
We've now spent the last 20 years really trying to pull that history back together, and that's not always easy.
General Electric, they still have power plants on the river, and as a byproduct, they created these things called PCBs.
How do we get the information to people that can make decisions about, we're gonna clean this place up?
I think it's really important that we're doing this.
And you see, look at having these kids work, they're not in the streets.
We wouldn't exist without water.
Our planet suffering, we have to care about water. What is the power of people to make a change? You know already.
All right, so sorry, that was a double view, but I can post the link to that video if you want to be able to see it a little bit better. So for this project, we included the science fellows and included microplastics as an element in the drinking watershed. So we focused on samples from the Tomhannock Reservoir, shown here, and then some of the tributaries to that, and then also looking at drinking water in Troy. So the samples I'm going to show you today are mostly going to be from these 4 locations. I'm going to show you 2 from the reservoir, one from East Reservoir, one from South Reservoir, and then I'll show you samples of 2 of the tributaries. Otter Creek, which is right here, is mostly agricultural and somewhat forested in its watershed. And then the Susquehanna Creek is more agricultural. It's about 40% agricultural. And then it also has a very busy road that's running along it. So if you've taken Route 7 through Troy to get to Vermont, you've passed where we sampled. So the methods we took, again, we're really thinking about what was the volume of water we would need, because this is a community science lab. The goal is to be able to empower people to go and collect their own samples. So we want to know, would 1 liter work? Is that enough? Do we need a larger sample to get a representative sample? And in the literature, there's a discussion about grab samples versus using net samples. So we were comparing the net samples to the grab samples. The data I'm going to show is just going to be the grab samples, because the net sample had so much organic material that through many, many iterations of digestions, it's not very reliable still. And I'll show you one image that shows some of the organic matter still present. And so these images, again, were taken by Allie. Allie, are you on? I'm gonna check and see. I don't think so. Okay, well then I will do my best, but know that a lot of what you'll see are images that she took. So in addition to just going out in the field and collecting our samples, and having high school students come out in the field with us, a number of artists came out. And so some of these artists were PhD students at RPI, some were other artists working in the area. Here's an image of a visiting artist from Spain who was assisting with sampling. And having artists in the field really allowed a new perspective to the process of sample collection. It also allowed there to be high quality images, which is great for students now that we're living in this very digital world, to be able to show what they're doing. And for us as scientists to have these great images of being out in the field. And one of the things I didn't realize before doing this and having artists come out in the field with me was this intersection between science and art. How taking a sample is knowledge. It's knowledge about the environment. And so we can expand this knowledge by bringing other people into these environments with us. All right, so we got back to the lab after taking our samples. Before I actually start showing what was in those samples, the big thing that happened was we realized that contamination was really hard to control. We couldn't constrain it. Plastics are everywhere. And so the process I was using to process the samples was to take the samples from the field, to filter them, to just have the plastics on a sieve, and then take those sieve samples and digest them to remove the organic matter, and then take that sample, transfer to a Petri dish and look in the Petri dish. But that involved a lot of use of other water for transferring, for working with the digestion. And one of the first findings, or one of the first things I realized, was that the DI water on campus had a lot of plastics in it. So as someone who has a background in aqueous geochemistry, I looked at the ion chemistry. We've removed the ions from solutions, so I'm used to just using DI or millipore water to proceed, and that's my pure water. But in fact, while it may not have those ions in it, they have been removed, there was actually a lot of plastics. And so the DI water is in this light blue color, and there were a ton of fibers and fragments. And aggregates is when the plastics were all together and we couldn't separate it out to say how many fibers or how many fragments there were. So then I was like, okay, well then let's just use a filtered tap water. And so that decreased our plastics somewhat in some of the categories. But then because we were evaporating the samples, we had a lot of ions, there was salt obscuring everything. So then we had to use the DI water and then filter that. And that's how we got the lowest amount, or to try to have our pure but not really pure water for samples. The other thing was every time we were processing samples, I would leave out a clean Petri dish in order to collect just what were the plastics in the air that were falling into that, so just as a sense of what is the air contamination. And every time the lab air had microplastics as well. So to keep in mind as I start showing you some of the data is that there was plastic everywhere. So here's just a few samples of the air deposition. So again, this is just leaving a Petri dish out on the counter while we were working in the lab and while running a air purifier as well. And so each of these little bits, so here's a little fiber, here's a little film, another fiber. These are all in millimeter scale, and down here they're in a smaller, the scale is in the, I think that one is, yeah, that's a smaller scale. Some big blue fibers as well. Pretty sure all these blue fibers are from jeans. We tried to have everyone wear cotton as opposed to synthetic materials. So many of these may not actually be plastics, but they are anthropogenic fibers. Okay, so moving on to some of these results, keep in mind again, contamination everywhere. So can't say too much beyond just that every sample we looked at had plastic present. So all samples contained microplastics. This were the total microplastics identified at each location. So a total of 9 liters of water was taken from each location. Fibers made up the majority of what we were finding, and then all other particles are lumped together in the yellow. The contamination of the double filtered water could be upwards of 100 microplastics per liter sometimes. And so that means it's possible that for the East Reservoir, South Reservoir, Otter Creek, that what we're showing here is mostly just contamination. However, the Sunsaconna Creek went above the amount that we'd seen in contamination. So this is the location that was by that really busy road. It's an agricultural region. So this could be a location where there is a large input of plastics to the reservoir. So then when I try to normalize them to their sample volume, so the sample volumes we looked at to think about what would be volumes for community scientists were 1 liter, 3 liter, 5 liters, just to see, is there a trend? If you collect more water, do you see more plastics? And it turns out there was no clear trend at each site. Sometimes the 5 liter sample had more, sometimes the 3 liter sample had more. I think this just really goes to showing how spatially diverse plastics are in the environment. So at the same location, the same time, you could have more in one location than another. And then again, a lot of this could be contamination too, because when you look at these counts, we're down into perhaps from normalizing for volume into the 20. So that could be contamination. And I really want to show you images of these. And so these images are taken from a stereoscope microscope post-processing. So this is where you can see that not all the organic material was digested. Here is some like leafy material, twiggy material still remaining. This is what we might have called an aggregate as well, because you can see there's a lot of fibers together. But sometimes we would have individual fibers or bits of fragments. And again, all of these images are from Allie. When you see one that looks like this, those are my images. You can really tell the difference. And again, these are some other stereo microscope images. Here is a film and some fibers, some more fibers. Here's a fiber that has some organic material on it. And so one of the things that came out of this project was Allie put together an installation with our images and some water samples at a gallery that spoke to domestic spaces. So this exhibit was called Plastic Kinship. It was part of the Flow exhibit in 2023. And it shows prints of these microscopic images with water samples that are in mason jars like we collected our samples. And they are all on waste countertops. So I'll read some of what she wrote. Domestic materials, countertop photo frames, imply the place of waste in domestic space and in our daily lives. While we take seriously and advocate for holding plastic producers accountable, panic and purity mentalities about microplastic leads to avoidance of the material realities of an already toxic body. And I'll show just a few more images. And again, Allie, if you jumped on, please unmute and say things. These images have been retouched. I do know that, but so here's some more of these images. There's some films. By retouching, you can really start to see how we can turn these microscopic images into more, think about what is the difference between an image for science, an image for art. Is there a difference? And so, yeah, thinking about what is the production of natural in scientific knowledge. And this is something that Allie and I have been talking a lot about, thinking about, are the plastics natural because they're in our environment, they're in our bodies? How do we decide whether a picture is an accurate rendering of nature, or the photo maker must then decide on what nature is first. So to return to our samples, I'll show now some of my images, again, with some scale behind some of the really photogenic fibers, a purple, a really cute little orange one, and blue. So these are some from tap water. So again, the project was twofold, looking at what is the source to the water treatment plant, and then what's coming out in the tap. So these images, again, are taken with a stereo microscope, and these are at millimeter scale. And every tap water we looked at had microplastics present as well. And so with that knowledge, we tested commercially available filters. I didn't want this project just to be alarmist, because there was a community component to that. So we wanted it to be informative and provide actionable items. So all of these filters that were chosen were ones that we were able to get at Amazon or Target for $60 or less. And at the very top here is showing, so blue is fibers, fragments are in yellow, the count, and this was for, I believe this was a liter, the count. So tap water had quite a bit, over 100 of fibers. And then as we looked at these different filters, it did decrease, but not for all of them. The Puro one is something completely different. I actually think a lot of this was the way they filter, that we had all these little black particles in it. And now that we've looked at that a little bit closer, I think it's actually charcoal. So some of them did decrease, but not all. Ironically, by looking at LifeStraw glass and plastic filters, the one that was the glass had a lot of filters in it, more so than the plastic. So this could be from contamination or from the filter itself. Even the glass filters, the container that was glass, the actual filter part inside had plastic as well. So this project has been ever evolving. So once recognizing that there was just so much contamination, it led me to think about, well, can we actually say anything about what is the amount of plastic in any of these samples? Maybe the better thing to think about is, what is our exposure to microplastics? Can we control our environment? And as I've done this project, I've been noticing plastic more and more everywhere. So like the broken eggshell at one of my sampling locations, oops, to having a baby shower and all of our gifts being sent to us, and just the amount of plastic coming in through shipping materials, just as one personal example. And so I've started rethinking what might be another approach to this. And so in considering exposure, I decided to start looking at small aliquots that are easy to think about. So something concrete, like a sip of water. So if you're wherever you are, if you're taking a simple sip, each of our sip varies in volume depending on the vessel. If you have a straw, no straw, how thirsty you are, etc. But most work suggests that the average sip is somewhere around 15 to 25 milliliters. So I looked at a 20 milliliter aliquot of different beverages that you might find in a kitchen. And these were all things that were in the Nature Lab kitchen in Troy in May 2024. So 20 milliliters was poured into pre-cleaned Petri dishes, and then I evaporated them in a closed incubator, and then we looked to see how many microplastics there were. And I'm showing just the fibers because mostly it was just all fibers we found. So tap water, from the lab, from the kitchen, bottled water had the most. Bottled water in most studies, like in a plastic bottle, has the most microplastics, which if you think about when there's a water crisis, either I've seen this with like PFAS or with lead, the solution is let's get bottled water. And so we think of bottled water as being the safe option when we don't trust our water treatment process. And in fact, while it may not have the lead or the PFAS, it does have a lot of plastic. So what are the choices that we're making to be able to have what we feel will be like the most clean and pure water? We even looked at a can, sparkling water. This was a Nature's Promise sparkling water. And I also took 1 cube out of a blue ice cube tray as well. And all of these had fibers present. So these images I'm going to show you are not retouched. These are now taken with a polarizing light microscope at 40x power. And so again, one of the things I've been discussing with Ali is the subjective production of scientific images. So images with the aesthetic of the scientific are read as more true or more objective than the artistic images. But the images are not the final objective truth, but a long process of subjective interpretation by humans. So if you've ever used a microscope, you think about all the choices you're making, especially if you're using a polarizing light microscope, turning the polarizer on, choosing the objective, what is the light you're going to use? If you're going to use the clear light or more of a yellow light. There's all these different choices we make when we're looking at slides under a microscope. So that was from the sparkling water, was a fiber. This was from the blue plastic ice cube tray, another fiber here. You'll note to see that there's some bubbles around that. That's because we used a tape to put this on a slide to be able to secure it. Here's some other images. The ones in the black over here, I believe those are the stereoscope images. The one from bottled water. So around this is just a bubble around this. And so Ali writes, references to the Mona Lisa and microscopes conjure many associated ideas when they're mapped as fitting exclusively into the categories of art and science. And let me show you a few others. So here's another one from bottled water. And this is probably my favorite image of the bottled water. And so when we take these images and think of them as an artwork, we think about the inescapability of exposure to microplastics. They're found in our bodies from birth. They've been found in placenta and in baby's blood. And so Ali writes that it's the new original sin. And so we're going to have to reckon with a kind of kinship with plastic ecologies, what intimacy with this material means. And so, as I've said, this is a constantly evolving process, which is really different than a lot of the other research I do, where the protocol is known, you go out, you take your samples, and you process them in the same way as other researchers, so we can compare and contrast findings. Instead, this really feels like this new frontier and constantly changing and modifying the process, which really brings into question if there are results or if the process is the result. And I think that's why having the community science element included within this and including artists really changes what is the end product or the result. Because if plastic is everywhere, is just identifying where it is very meaningful, or is the outreach and the exposure element the most meaningful? And so being concerned with contamination and talking with people working on microplastics, we are changing protocols again, using this forensic tape onto filtered samples instead of digesting and evaporating water. So this will be this summer with the Water Justice Lab Science Fellows. So I didn't go out in the field with them last summer. It turns out they were bummed that they didn't get to do microplastics. So we will return again this summer as part of their camp and do microplastic sampling with a little bit of a different perspective, thinking about the Upper Hudson and what might be different sources. But a big focus will be the community involvement. So some elements that we're hoping to bring in is to work with another artist in Buffalo who has made these microplastic collection bins and for us to put a microplastic collection bin as part of the Sanctuary for Independent Media art trail. So then we can take these plastic pieces and use them to then make mosaics, get people involved in going out in the field, collections, and discussions. And continue to host events and screenings and exhibits that involve the community. So here's one example of that. This is an exhibit from last semester at the Sanctuary for Independent Media, showing some of these images up on the wall. I believe these are still on exhibit. I'm not completely sure, but this was called Microplastics, a BioArt exhibit. So these 4 that you can see are the ones that Allie took, and we printed out really large. So a big part of this is scale, taking something that we can't see and then blowing it up so that you feel it around you and can really envision and see what it is. And by adding on the polarizing light, it gives it these really beautiful, bright colors. So I'm checking for time. I do want to mention a couple other things. So by including artists, your work can be transformed in so many ways. So here is an exhibit that Allie had recently that included microplastics. That was called Transcorporal. I'm going to just show you a video from this. So these videos, she did some live microplastic video projections. And also people were able to interact with the microscope and look at these samples that we had collected through the microscope as well. So let me show the projection first. So that's over here. So on this big screen, you can see this is the projection of 2 fibers. There's a lot of other things going on as part of this exhibit. There are these big, huge screens that were also plastic with these images of microplastic projected on them. But this is the live microplastics video projection. And then this is an image. Oh, we'll talk first. So this is someone with their phone looking through the microscope, investigating the slide. All right. So with that, I just want to mention that there were a lot of people involved with all of the sample collection you saw. Many of these are high school students. In this image, you can see some of the summer youth fellows who are out in the field. Here's Ellie, Kathy High, one of RPI undergraduates, EP, and then many other students were involved, many RPI students, other media interns and youth science fellows at the Water Justice Lab as well. And with that, I'll take questions. Thank you.